Hello, class. I'm going to attempt to finish up the notes that we started in our class on Friday. So I will be using this handout that you received. And just to remind you, we are in Chapter 5. We're working on finding the area under the curve. We have talked about how in a data-driven problem like this one, you plot the points, then you divide it into whatever units you're asked to divide it into, and then you draw your line straight up. And if you're doing a left sum, then you use the points on the left side to form your rectangles. So in this problem, we were doing L4, which meant when I plotted the curve, I wanted to go from 12 straight up and then split it into 4 pieces. And then once I put those points onto the curve, I draw those parts this way, okay? And then you're dealing with rectangles that will approximate the area underneath that shape. So this will be 3 times the height here, 3 times the height here, 3 times the height here. And so that's how we turn it into this. We wind up using all of these points except this last point because it's a left sum, and then we can factor out the 3 and we get our feet in this problem, okay? In this problem, this was representing distance, so our units are going to be feet. When you did the right sum of the same thing, we used the right points. So the one that got left out was the point at 0. We did this in class. And then we did a midpoint in this case, but we only divided it into 2 sections. And that made our heights the middle numbers in the chart. So that one and that one, you can see how that's worked out. Just to review. Okay, turning the page. Then we were actually looking at different notations that are used. So this is find R6 for this function, which means that we graph the function and then we divide it into 6 pieces, and we divided it into little pieces like that. We actually had to evaluate these. And then remember that delta x is b minus a over n, which gives you the width of one of your little partitions. Okay, that may come in later handy. Okay, so notice that our last one, the height was 0, and that was our answer. And then we went on over and we did a couple like this. We talked a little bit about what's called signed area on this last problem, although we were really just getting used to drawing this from negative something to something. Okay, so we graphed tangent, which has asymptotes at negative pi over 2 and pi over 2. And the part that we were concerned with were from negative pi over 4 to pi over 4. So I probably could have labeled those pieces like that. And then in this case, these would cancel and give us an area of 0, although it didn't ask for that. And then in this case, we drew this one from pi to 2 pi, talking about the sine graph. And then we're shading this underneath this x-axis, which means that that would be a negative signed area. We only had to draw it in this problem, but it would come out negative. Okay, moving on. This is kind of where we ended class. We looked at this notation where this is the sum of the partitions. This is the height value, and this is the partitions that you're adding. So this will be the base of your figures, and the sum of the heights all the way to over how many rectangles you have. And so in this notation, this is the, we're dealing with the Riemann sum of the function f with partitions, p, or points, and c stands for, it says function, partition, and C stood for the choice of sample points. So in the problems you run into like this, they're actually giving you the points that they want you to use. Okay, so we started out, I'm doing problem 21, I'm skipping 20. Okay, I only did 21 because it's simple to graph. If you do something like number 20 in your assignment, you're welcome to use a graphing calculator to graph it and plot some points. In this problem, here is the sine graph. It tells me I want to use the points pi over 6, 0, pi over 6, pi over 2. So I've labeled those x values. Those are the points that I'm wanting to deal with. And C stands for the choice of sample points, which means in this case, we're going to be looking for 0.4, 0.7, and 1.2 on our graph. Okay, so then we actually have to kind of estimate some of this. So something like this, for now, let's just use a calculator to think about it. If you do pi over 6, that's 3.14 divided by 6. It's approximately 0.5. So this is an approximation. If you do pi over 3, this is almost 1. If you do pi over 2, this is about 1.6, okay? And so when we go to put those points on our graph, we have to kind of estimate where they would fall. And so on this one, we're going to put 0.4 here. So this is kind of a strange situation because they are not points that are on our graph. We're actually locating spots that we have to find the point that corresponds to it on our graph. So we'll come over here and say 0.4 will correspond to whatever the sine of 0.4 is, okay? And that'll be your y value, okay? So you're gonna do that with 0.4, 0.7, 1.2. So 0.7 might be about right here. 1.2 would be somewhere like right in here. And so the corresponding heights are gonna go up from there and up from there, okay? So how we already separated it, we could go ahead and draw these straight up. Okay, it's hard to draw while I'm holding my phone, hold on. Okay, so if I was to draw that straight up and that one straight up, okay, I actually have drawn it from pi over 6, pi over 3, and that's dividing it into 3 sections, but the heights are dependent on these numbers, okay, which means I'll come over here and I'll make a height here and take it over, and that rectangle will be that, okay, then I'll do the same here, take it over. So this is a little different, and we'll shade. Okay, same thing here, take it over, it's going to come a little above there, and so draw it like that, okay? And then what you've done is you've set up pi over 6 as your base, the height being whatever that function value is of sine over pi over 4, okay? And then you're going to do, this would be pi over 6 in width, and then sine of pi over 7. Okay, so it comes out looking like that. And you would need a calculator to get your answer on that. Okay, so that's kind of how those work. Turn over your page and let's do a little bit more exploring. Okay, so if you go to the next part, we're going to look at Riemann sums and a few other little properties that you run into. Okay, so first of all, Riemann sum and definite integrals will have numbers at the low point and the high point. And so this will be like your left point and your right point on the function, kind of like we've been doing, okay? So if you go from A to A, the integral value is going to be 0. Fill that in, okay? If you have a number in front of the function, one of the properties is you can bring the number outside of the integral, then figure out whatever that integral is. Okay, and we're going to be getting that area and then multiplying by that constant number, okay? Also, if you have something like B and A backwards, for instance, if something is like reversed from how they sit on a number line, let's say it went from -5 to 3, I'm sorry, let's change it to negative, let me change it, I'm sorry. Okay, let's just say it went from 15 to 3. That's not how you think from left to right. When you change it, you are allowed to move it around if you bring out a negative, so this would be how you change it. And that's what this property is saying, is that if you reverse those numbers, you still do the integral the same way, but there's a negative value in it. Okay, so add that into your notes. Okay, all right, let's go on over here. If C lies between A and B, then you can actually add the pieces. If you have two functions in parentheses from A to B, you can actually add the integrals of the sums. So let me just show you this and you can write those in. Okay, so you're gonna have A to C of f of x in an integral plus B to C of f of x in an integral. Then you're going to look at this one and you can say you can do from A to B of the function plus from A to B of the other function. So you can separate them like that. You can also do that with subtraction. So this would be that first function's integral from A to B minus the second function integral of A to B, and you bring over that dx every time. Okay, so using those functions, let's get to work. Okay, so we're gonna sketch and evaluate using geometry formulas, and you're gonna see that in your classwork assignment as you work. So in this problem, we're gonna sketch it thinking 4 is a function. It's actually y equals 4. If you draw it, you're gonna go 4, and it's a horizontal line, okay? If I want to get the integral from 1 to 6, then I'm gonna go from 1 to 6, and I'm gonna bring this straight up, and I'm gonna form a rectangle, okay? The area of this rectangle is gonna be 5 times 4, so this is gonna equal 20, okay? That's kind of how that works, okay? So this is all dependent on you being able to graph these. Now, as you do these, you should be doing these with no calculator, okay? So only the ones that had the sign values you were doing should you use a calculator. On these, you should be able to graph these with your brain, okay? So this is gonna be y equals x plus 2. So you can go to y-intercept of 2, put your point. You're gonna go up 1 over 1, and you're gonna keep going until you get to 3, because this is going from 1 to 3 from left to right, because this is from 1 to 3. So you would want to plot the point 1, 3, and the point 3 plus 2 is 5. Okay, so it winds up looking like that. And this is a line, okay? And what you wind up with is that shape, okay? That shape is a trapezoid, so you would do 1/2 the height times the sum of the bases. 1/2 the height times the sum of the bases. You may see some problems like this in your classwork assignment. The height here would be 2 if you flip this over. That's the trapezoid. Your base heights are 3 and 5. So then you would wind up with 8. So this would be 1/2 the height of 2 times 3 plus 5. Those are the parallel base lengths. And it would normally be on the side like that, okay? And then you would get that answer, and the answer is 8, okay? All right, this one is a little bit harder for some people because you don't really recognize what it is, but this is actually the equation of a circle, and it's only the top part, okay? So if you think about just plugging in some values, if you put in 0, you get the square root of 4, which is 2. If you put in 1, you get the square root of 3, which is somewhere like right in there. If you put in -1, you're gonna get the same thing, that height. If you put in 2, you're gonna wind up with 0. And then here, And this is a function that represents just the top half of that circle. And so that's your area you want. So this is going to be 1/2 pi r squared where the radius is 2. 1/2 pi r squared where the radius is 2. So that would be 1/2 of 4 pi, which is 2 pi. Okay, so we are looking at signed area. So when you do one like this that's broken up into parts, you're actually doing the area that goes back to the x-axis. So this triangle's area is going to actually be negative. This triangle's going to be negative. This one's going to be positive, and you're going to add all those together. Okay, so you're going to wind up with this. I'll let you try to do it, but you wind up with 1/2 base times height, make it negative, and you see what I'm doing on those. 0.5 is what you should get. Okay, likewise on this one, this is going to be a negative half circles area. This is going to be a positive half circles area. So you wind up with this 1/2, this, and then this. And then you would actually add these together. And so this would be negative pi over 2. Okay, so let me see if I can do this. So negative pi over 2 plus 2 pi, because we did their areas here and here. And so this answer would come out to be 3 pi over 2. Okay. Now, when you go to do these last ones, we're using those properties from 0 to 2 of the function f of x. Oh, I'm sorry, this goes with this, so I did too much. So here's the answers. I did too much. All of these went with that. So you wind up with negative pi over 2, which I showed you. And from 0 to 6 is 3 pi over 2. 1 to 6 would be 9 pi over 4, and then 3 pi over 4 is this one. Okay, and so that should get you through almost everything. Let's look at one more. Also be aware that you could run into something like this problem where you're given two different integrals and you want to actually find some different things. So if you notice that you're given from 0 to 3 of the same function f of x dx, and you're given from 3 to 7 of f of x dx, to get 0 to 7, you can just add these values, 4 plus negative 1. This one you can do 2 times 4. This from 7 to, not 4, but this would be from 3 to 7 because the integral is from 3 to 7. This one would be 0, and so here's your answers. Here's the first 2, and there's the second 2. Okay, and that's what you're going to be working with today. And I want you to complete your classwork assignment that you find and catch up on any of the other assignments that I extended time on today. We will move on tomorrow in class. Hopefully the weather will be better, but I will see you tomorrow.